Hey everyone, I'm Erika.
Zee.
Hey, I'm Keisha.
And today we're going to be talking about factor groups. So today we're going to be talking about our factor groups, which are also referred to as quotient groups. Now, the definition for a factor group is when we have a group G and when we have a normal subgroup H of G. Now, the factor groups is denoted by this slash, but we read it as G factor H, which is the set of cosets of H and G. Now, the elements of G factor H are written as H times A, which is our subgroup H times a coefficient A that comes from our group G. And that forms a group under normal operation on our subgroup H on our coefficient A. Thus, we have HA times HB, which gives us HAB. Also, we have a function mu, which maps the G factor H to phi of G here, which is defined by mu of A times H, which equals phi of A, which is an isomorphism, where both coset multiplication is well defined as well as mu. Now, when it comes to identifying elements of a factor group, we can start by computing the direct product between all of the groups that are being multiplied together. That result will give us a new element consisting of elements from our previous groups based on position.
All right, so I already wrote down a factor group. I have Z4 cross Z2 factor H, and we have 2 and 1. If we take the elements of Z4, we know it's 0, 1, 2, and 3. And if we take the elements of Z2, we know we have 0 and 1. Now, when we cross Z4 cross Z2, meaning we have 0 and 0, 0 from Z4 and 0 from Z2, we produce an element of 0, 0. And we do the same thing again for 0. So we get 0 and 1. We're going to do the same thing for each element in Z4. So we're going to do 1. We get 1 and 0. We're also going to do 1 and 1. Then we're going to do it for 2 as well. We get 2, 0. Then we're going to get 2 and 1. Then we're going to do our last element of Z4, which is 3. And then we're left with 3 and 1. Now, so if you notice, we can note that Z4, the elements A are coming from Z4, and we can also know that B is coming from Z2. Now we can put our H into play. So our H is 2, 1. So we're just going to write this all the way down, right next to our Z4 cross Z2. Okay, once we have that written down, now we can do some type of algebra. Okay, our first operation is addition, but we have to keep in mind that we're doing Z addition modulo 4. So our first one is going to be 0 plus 2, which gives us 2. That's fine because we're within 0 and 3 for Z4. Then we're going to do 0 plus 1, gives us 1. And then we're going to do the same thing. The 1 came from the 0 plus 1, and it's fine because we're working with Z mod 2. All right, so the second one we have 0 plus 2, gives us 2. Then we have 1 plus 1, gives us 2. But we're not going to write 2 because our operation is addition under modulo 2. So we're going to subtract 2 from 2, which will give us 0. So now 1 and 2 gives us 3. 0 plus 1 gives us 1. Now 1 and 2 gives us 3 again. And 1 and 1, we discussed that we're going to do 2 minus 2. Then we're going to do 2 plus 2, which is 4. But because we're, with the respect of, we're in mod 4, we're going to subtract 4, which is going to give us 0. And then we have 0 plus 1, which is 1, which is fine. And then again, 2 plus 2 is 4. We're going to subtract 4, which gives us 0. Then we have 1 plus 1, which gives us 2. And keep in mind that we're addition under mod 2. We're going to subtract 2. This is going to give us 0, 0. We're going to do the same thing here. 3 plus 2 is 5. 5 minus 4 is 1. Then we're going to do 0 plus 1, which is 1. That's fine. We have 3 plus 2. Subtract 4 from 5 gives us 1. And 1 plus 1 gives us 1. So note that these are all the elements for our factor group Z4 cross Z2 factor 2, 1. Note that there are 8 elements. 1, 2, 3, 4, 5, 6, 7, 8. Before I move on to the next question, I wanted to show that our formula, AH times HB is equal to AB times H. It was 8 elements here, but I erased the last 4 because I forgot to show this very important concept. So if you look at it, remember when we did Z4 cross Z2, we were able to produce 8 elements. So let's say we know that this 0 right here, for example, comes from Z4, and this 0 comes from Z2, and this is our subgroup H. Now, if we look at our formula, we have A right there from Z4, and then we have B from Z2, and then we also have our H. So we have H times A, and then we also have H times B. Now, when we do our operation, which is our mod 4 and our mod 2, we got back 2 and 1. So hence, we were able to rewrite our elements in H times A times H times B is equal to A times B times H. Okay, so now we are going to determine the order of the factor group. So once again, we're going to use the same factor group, and to determine our order, we're going to use this formula. And this formula basically says the set Z factor NZ, and NZ is represent the cyclic subgroup generated by N, is equal to Zn. Zn is noted for integers mod on N. So we know that Z4 cross Z2 is our Z in this case. So we're going to put it into our formula. Then we know that our cyclic subgroup generated by N is coming from our subgroup here, H. And then this is going to equal to our Cn. To find our order, we're going to find the order of each of these separately. So we're going to find the order of Z4 cross Z2. There's 4 elements in Z4. We said in the previous element that it was 0, 1, 2, and 3. And there's also two elements in Z2, which is 0 and 1. If we do 4 times 2, which is equal to 8, that'll give us the order for the top part. Now we have to figure out how to find the order of the cyclic subgroup generated by 2 and 1. So what we're going to do is going to find the order by adding 2 and 1 until we get back our identity element, which is 0, 0. So 2 plus 1, for the first time, it's going to equal to 2 plus 1. Then we're going to do 2 plus 1 plus 2 plus 1. Alright, keep in mind before we add, we need to note that we're looking at Z mod 4 and Z mod 2 when we're adding them. So when we're going to add the first part, 2 plus 2 and mod 4 is going to give us 4 minus 4, And then 1 plus 1 is equal to 2, but since we're in mod 2, we're going to subtract 2, which is going to give us 0. So hence we get back the identity element. So this is giving us our order. So our order for this part is 2. So now we have the order for the numerator, we have the order for the denominator. So if we do 8 divided by 2 is equal to 4. So our order is 4. Alright, so we're going to do something else. We're going to do comparing number 3 and comparing number 4. If you look at number 3 and number 4, they both have Z, the set Z. Number 3 has 4 cross Z2. Number 4 has 5 cross Z3, which is fine. Then our second subgroup generated by N, in our case for number 3, we said it was 2 and 1. But for number 4, it's 0 cross Z5. And if we do 0 cross Z5, that's going to give us more than one subgroup. So this is our element 0, and we're going to cross it to Z5. So we get one element here, another one, and we get up to 1, 2, 3, 4, 5. We get up to 5 elements, and these 5 elements are now our subgroups. So the difference between these two numbers is that for number 3, we only have 1 subgroup. And then for number 4, we have 5 subgroups. So like I discussed in the previous problem, I think problem number 2, how we use the binary operations, we did 0 plus 2, and we kept in mind that we're in mod 4, which gave us 2. And we were fine because 2 is an element of Z4. Mod 4. And then we did 0 plus 1, which gave us 1, which is fine too, because it was an element of integers mod 2. So that's how the binary operations work.
Now I'm going to combine 2 elements from our factor group using our known binary operation, which is modulo addition. So I'm going to take 2 arbitrary elements and just add them together to see what I get. I'll take 2, 1 and combine it with 1, 1. So if I have 2, 1 and 1, 1, and I add those together with modulo addition, 4 and 2, that will give me 3, 2, which is 3 in mod 4, but 0 in mod 2. Another example could be I'll take 3, 0 and add 2, 0, and that'll give me, under modulo addition, 5, 0, which is the equivalent to 1, 0 in our factor group.
Hello guys, Z here. So what we're going to do, we're going to take an element and we're going to find the order. And when we're choosing our element, we don't want to choose the identity element. So let's go with 3, 1. So we know the objective of an order. We're going to see how many times it takes us to get back to that element. Hello guys, Z here. And for this part of the podcast, we're going to focus on finding the order of an element of the factor groups. So we don't want to choose the identity element. So we're going to just choose the element. And let's choose 3, 1. Alright, so we know the goal of, to find the order, we want to figure out how many iterations it takes to get back to the identity element. Okay, so what we're going to do is going to take our element that we chose and we're going to add it to itself. Alright. 3-1 plus 3-1 gets us 6-2. And keep in mind that the element has to fall under the direct product of Z4 cross Z2. So in this case, 6-2 isn't a part of this. So this translates into 2-0. Alright, so 2-0 isn't the identity element, so we'll add 3-1 again. Here we have 9 and 3. 9-3 translates into 3-1. Alright, so again, we don't have the identity element, so we'll add 3-1 again. Alright, so when we translate 12-4 in order to fit into Z4 cross Z2, we get back 0, 0. 0, 0 is the identity element. So this 3-1, it has an order of, let's count, 1, 2, 3, 4. So we write this as 3-1 because this is the element we were dealing with, and we're gonna draw absolute value signs around it. That's the symbol for order. So we read it as the order of 3-1 is 4. So next we're going to talk about non-factor groups. We already talked about factor groups and how we find the elements. So let's say we have the group with elements 0 through 6, which is also known as Z7. And we have the subgroup denoted by H, which is 0, 2, 4, 6. We can tell that it's a non-factor group because our H in this case is not a normal subgroup. We know this because we're going to take both the left coset and the right coset. Alright, and we did that here. And here we can see that our cosets, our left and right cosets are equal. However, the elements that we obtain from doing the cosets don't fall under Z7. So, for example, we're looking at the 2 plus H coset. We have elements 2, 4, 6, and 8. 8 isn't a part of Z7, so this makes this, well, it's not a normal subgroup. Alright, lastly, as we get ready to conclude our podcast, we were going through our checklist and we realized that we failed to mention a topic, so we're gonna go back. And as you can see, we're dealing with a previous example, and these were the elements we got for the factor group here, this factor group. And you may notice that we're missing an element, and it's because the element we're missing is 1, 0, but it's already, we have 0, 1, and like you really don't have to write the 1, 0. It's pretty redundant, but yeah. We wanted to find an element of the factor group that is not in our list of elements. So let me clarify. We want to find an element that is not in our factor group, and let's say 5, 4. The element 5, 4. 5, 4 isn't an element of our factor group, simply because as we pay attention to the order of the elements, 5 isn't nowhere in Z4, and 4 isn't anywhere in Z2. And basically the reason that the element 5, 4 would not be considered an element of our factor group is simply because, 5 4 isn't closed under the direct product of Z4 cross Z2.